Hello everyone, I'm Joey Gatto, and my NSF-RU research project was called Stacking versus Deep Learning. It's a very fancy title for something that was essentially optimizing image classification technologies for computer vision. So first I'd like to discuss a little bit just how does a computer learn? Computers learn very similarly to how humans learn. So a computer will learn from past experiences. Giving information about the past, what does the computer think will happen in the future? If you give it past examples, it can make predictions about the future. Learning to recognize patterns. Just like when we're presented with a new situation, the computer can look at random data and decipher patterns within it and help it make inferences. Also learning from reinforcement. While just like us, updating our knowledge or updating our algorithms as we gain new information about a situation. So here's an example of an image classification algorithm in a self-driving car application. As you can see, it's very easy for a computer to notice lines and to notice curves and edges and colors, but high-level abstractions like, oh, that's a lane, we have to stay within this lane to know what a lane is, or oh, that's a car, we're this far away, this is what a car does, stay away from the other car. Those kinds of inferences are very difficult for the computer to make, and that's what computer vision is all about. So what's wrong with computer vision today? It's actually come a long way and it's very effective, but the issue is it's very computationally expensive. It requires a very fast computer to run. It's very difficult to implement. It's very hard for a new computer scientist or statistician to implement any of these algorithms, and they're also very difficult algorithms for humans to interpret. The state-of-the-art algorithm for computer vision technology is called a convolutional neural network. This is a representation of a convolutional neural network. As you can see, it doesn't make much sense to the layman, unlike other machine learning algorithms, and it's very difficult and expensive for your computer to run. Average computers cannot run it. Here's a picture of my computer running it. This is a real image, not something I took off Google. So the goal of my project, Stacking versus Deep Learning. First of all, just to explore the effectiveness of various image classification models. There are many different ways for a computer to look at an image and make a decision. And we wanted to look at all of the different algorithms and see how effective they are in different data sets. Discover an alternative image classification model that's good enough. We don't anticipate to outperform the convolutional neural network, but for people who don't have the computational resources to run those kinds of algorithms, if they're only sacrificing 1 or 2% with our algorithm, it will be good enough for classifying images. And thus, that will make image classification technologies more widely accessible. Someone like me who can't afford a computer like that is very restricted in what I am allowed to do with my personal machine learning research. And also, we want to provide benchmarks for all of these algorithms, so how all different algorithms perform on different data sets and how efficient they are. Our goal is to hopefully discover a model that is much more efficient than the convolutional neural network and is only sacrificing maybe 3 to 4% accuracy, depending on the data set, sometimes more, sometimes less. So the methods we're going to be using are feature engineering methods. So we're going to use restricted Boltzmann machines, autoencoders, deep belief nets, and random hyperplanes. And the stacking name of the project comes from stacking these different methods together, not just using them by themselves. So what is feature engineering? First, let's talk about how computers look at images. Here's a picture of a very adorable kitten, but what you may not know is you can represent this picture of this kitten with numbers. Each image is an RGB 3-channel image, and each number on this slide here, it represents how red that pixel is at the top left. So where it says 0.112 on the right side there, that's how red the top leftmost pixel of the image is. And once you feed the computer these arrays of numbers that represent images, it's much easier for it to make decisions about what's going on within that image. So here we have some image classification models extracting the most important features from the image. What feature engineering does is it reduces the data set by only letting the classifier look at the most important images. So when we put the data into an algorithm, yes, you could put every pixel into the algorithm, or just the shape of the eyes, the eyebrows, the nose, the mouth, the shape of the head. Those really define what's within the image, and it makes the whole process faster and more accurate. So this is just an example. As we reduce the size of our data, it will increase the accuracy since we're only using the most important features, and increase the efficiency since we're since we're reducing the size of our data set. So currently, we have many more data sets we want to test on. Right now, we've been working with the very popular MNIST data set. Using just standard linear classifiers like linear SVM or logistic regression, we get about 93% accuracy without using any feature engineering. But once we start using feature extraction techniques, we see a 4 to 5% increase in accuracy. And as you can see, it does not outperform the convolutional neural network, but we did succeed in providing a more efficient method to get high accuracy results without using the convolutional neural network.